Whenever I sit down and look at that number written in a textbook, 299, 792, 458 meters per second, I get this funny feeling in my stomach. It looks so incredibly precise, yet so completely arbitrary, doesn't it? It looks like a rule some policeman made up, a speed limit sign posted on the edge of the galaxy. You look at it and you think, well, 55 miles per hour is the law on the highway, but if I have a really good engine, maybe I can do 60. Maybe I can push it to 70 if I don't get caught. We're human beings, after all. We are used to pushing limits. We look at a wall and we want to climb over it. Think about the sound barrier. For years, people said you couldn't fly faster than sound, that the air would pile up in front of the wings like concrete, and the plane would shake apart. But that turned out to be just an engineering problem. We built a stronger plane with sweep, back wings. We put a bigger engine on the back, and boom, we went faster than sound. No problem. So it is perfectly natural to ask, why can't we do the same thing with light? Why can't we just build a bigger rocket, burn a fancy new kind of fuel, and push right past that number? But you see, nature is playing a different kind of game than we are. The speed of light isn't a rule written on top of the universe like a law in a book. It is the universe. It's not a limit on how fast your car can go. It's a limit on how the road itself is built. Most people accept it just because Einstein said so. But that's not understanding. That's just repeating a catechism, like memorizing a poem in a language you don't speak. To really understand it, to get the kick of the discovery, you have to dig down into the guts of the thing and see where the mess is. You have to look at the problem the way we did before we knew the answer. When we were confused and things didn't make sense. Let's start with something you can see, something ordinary, something you deal with every time you get out of bed. Gravity. You drop a piece of chalk. Galileo watched things fall, and he measured it very carefully. He found that in the first second, anything you drop falls 16 feet. It doesn't matter if it's a heavy rock or a light piece of wood or a gold brick. If you take away the air resistance, it falls 16 feet in 1 second. That's a fact. Now, look at the moon. It's hanging up there in the sky, huge and heavy, going around the earth. Common sense tells you it's not falling. If it were falling, it would come down and hit us on the head. It looks like it's just coasting on a track. But Newton, he had this tremendous imagination. He dared to ask a question that nobody else was asking. He said, what if the moon is falling? What if the force pulling the apple down is the same force holding the moon in. Imagine you climb a mountain so ridiculously high it sticks out of the atmosphere, way up into space. You bring a cannon with you. You fire a cannonball horizontally. It goes forward, and gravity pulls it down. It hits the ground a few miles away. So you put more powder in. You shoot it faster. It goes further. It curves a bit less. But eventually, it still hits the ground. But think about the shape of the Earth. The Earth is a ball. It curves. If you shoot the cannonball fast enough, really fast, as it falls toward the Earth curves away underneath it. The ground curves down just as fast as the ball falls. So the ball is falling and falling and falling, but the ground keeps curving away, so it never actually hits. That's what an orbit is. The moon is falling toward us continuously, every single second, forever. So Newton sits down and does the arithmetic. He says, okay, we are standing on the surface about 4,000 miles from the center of the Earth. The moon is way out there, 240,000 miles away. That's 60 times further than we are. Now, Newton had a hunch. He thought, if gravity spreads out from the Earth like butter on toast, getting thinner and thinner the further you go, it should follow an inverse square law. That means if you go twice as far, the gravity is 4 times weaker. If you go 3 times as far, it's 9 times weaker. If you go 60 times further out, the gravity should be 60 squared times weaker. That's 600 times weaker. So, if the moon is really falling, it shouldn't fall 16 feet in 1 second, like the chalk does here. It should fall 16 feet divided by 600. You get your pencil out, you calculate that, and it comes out to about 1/20th of an inch. Just a tiny little nudge. Newton checks the geometry of the moon's orbit. He measures how much the path actually curves in 1 second, and lo and behold, it's exactly 1/20th of an inch. It matched. This was a terrifying moment for human thought. It meant the laws down here, the laws of the dirt and the rocks and the apples, were the exact same laws up there in the heavens. It tied the whole universe together into one big machine. This success gave us tremendous confidence. We got cocky. We thought we had the whole game figured out. We used this confidence to look at other things like the moons of Jupiter. They go around like a clock, tick, tock, very precise. You can predict exactly when they will disappear behind the planet. But a fellow named Romer noticed something about 300 years ago. He looked at his charts, and he looked at the sky, and things weren't matching up. When the Earth was close to Jupiter, in our orbit, the moons were on time. But when the Earth was on the other side of the solar system, far away from Jupiter. The moons were late. 8 minutes late. Now, if you were a bad scientist, you'd say, well, Jupiter's clock is broken, or Newton was wrong. But Romer said, no, the clock is fine. The was news is late. He realized that what we see isn't happening now. It happened a while ago. The light has to swim across the emptiness of space to get to our eyes. It's like sending a letter. It takes time to travel. When we are further away, the light has to swim that extra distance, the whole width of the Earth's orbit, and that takes time. This was the first time we realized light wasn't some instantaneous magic that filled the room the moment you opened your eyes. It was a traveler. It had a speed. And if it has a speed, you can measure it. And that's when the real trouble started. That's when the headaches began. Once you know light has a speed, you start measuring it in different ways. And you find something that completely insults your common sense. Imagine you are on a train moving 100 miles an hour. You have a baseball. You throw the baseball forward at 100 miles an hour to the guy standing on the ground. The ball is moving at 200 miles an hour. Velocities add up. It's simple arithmetic. 100 plus 100 is 200. So you think, okay, if I'm on a rocket ship going half the speed of light and I turn on a flashlight, the light should come out at the speed of light plus the speed of the rocket. It should go super fast, but we measure it and it doesn't. You can go as fast as you want. You can go 99% the speed of light, and you shine that light forward, and it still travels away from you at exactly c. The guy on the ground measures it at fc. You measure it at sc. The light doesn't care how fast you are moving. The speed of light is constant, no matter who is looking at it or how fast they are going. This drove everyone crazy. It broke the laws of physics as we knew them. How can two people moving at different speeds see the same beam of light going at the same speed relative to themselves? It's impossible unless something else is changing. Unless the stage itself is changing. Unless the ruler you are using to measure distance and the clock you are using to measure time are not fixed. And this is what Einstein realized. He saw that space and time are not a rigid steel frame. They are flexible. They are squishy. If you want the speed of light to stay the same, which nature insists on, then space has to shrink, and time has to slow down to compensate. It's like a conspiracy of the universe to keep that number, FCS, constant. When you move fast, your time slows down, literally. Your watch ticks slower than the watch of the guy standing still. Space squashes up in the direction you are moving. It sounds like science fiction, but we measure this every day. We have precise clocks on GPS satellites. They are moving fast, so their time is different. If we didn't program the computers to adjust for Einstein's relativity, the GPS would be off by miles within a single day. But why? Why this specific number? Why can't we go faster? Let's try to look at it a different way, maybe a geometric way. We are used to thinking of space as 3 dimensions up, down, left, right, forward, backward. But we actually live in 4 dimensions. The 4th one is time. And here is the secret that nobody tells you: you are always moving. Even now, sitting there in your chair, you think you are stationary, but you aren't. You are racing through time. You are traveling into the future at a steady rate, 24 hours per day, 60 seconds per minute. That is a speed. In fact, everything in the universe, you, me, the stars, the atoms, we are all moving through space-time at the speed of light. That is the constant speed of everything. But this speed acts like a resource that can be shared between space and time. Imagine a car that has a governor on the engine. It can only go exactly 100 miles an hour, no more, no less. That's the rule of the car. If it drives purely north, it makes 100 miles an hour of progress north and 0 progress east. Now suppose it turns. It drives northeast. It's still going 100 miles an hour total, but now it's splitting that speed. Maybe it's doing 70 north and 70 east. It's making less progress to the north because it diverted some of its speed to the east, you see. Now replace north with time and east with space. When you are sitting still, you are moving 100% through time. That's your maximum speed through time. You age at the normal rate. But when you start to move through space, when you get up and run, or get in a rocket, you have to divert some of that fixed total speed. You are now moving through space, so you must move slower through time. That's why time slows down when you move fast. You are borrowing speed from your time, motion to use for your space motion. You are rotating your direction in 4 dimensions. Now, follow this to the limit. What happens if you divert all your speed into space? You push the pedal to the metal in the space direction. You have no speed left for time. Your motion through time drops to 0. Your clock stops. That is the speed of light. It is the maximum possible speed through space because there is no more speed to borrow. You can't go faster than light for the same reason you can't go more north than north. You have used up all your motion vector. That is why light, the photon, doesn't experience time. It is born in a star and hits your eye 1,000,000 years later. But for the photon, it is instant. It exists purely in space, not in time. There is another way to look at it, a more nuts and bolts physical way, which involves energy. Einstein gave us that famous formula, energy equals mass. Usually, people think this just means you can build a bomb, but it means something else. It means energy and mass are the same stuff, just different labels. When you push an object to make it go faster, you are putting energy of motion, kinetic energy, into it. But since energy is mass, you are actually making the object heavier. At low speeds, like in a car, this effect is tiny. You can't notice it. But we see this in our big particle accelerators, the synchrotrons. We push little electrons. As we push them faster, they get heavier. Literally. Their inertia increases. It becomes a vicious cycle. You push the electron, it gets faster, but it also gets heavier. So now you need to push harder to get the same increase in speed. But pushing harder adds more energy, which makes it even heavier. As you approach the speed of light, the mass shoots up toward infinity. To get to the actual speed of light, to get to 100%, you would need infinite energy to push that infinite mass. And there isn't infinite energy in the universe. So, you can never quite get there. You can get to 99.9% or 99.9999%, but nature will just keep making you heavier and heavier. So you can never cross that line. It's nature's way of saying, that's enough. And finally, there is the deepest reason, the problem of cause and effect. If you could go faster than light, the geometry of space-time tells us something very strange would happen. You could send a message back in time. You could pick up a telephone that uses super light signals and call your grandmother before your mother was born. You could tell her not to marry your grandfather, but then you wouldn't be born to make the call. The universe seems to be built on a very strict rule. The cause must come before the effect. The glass must break after you drop it, not before. The speed of light is really the speed of information. It's the speed limit of reality updating itself. If we could break it, the whole structure of history would unravel. It's not just a speed limit for particles, it's the protection that keeps the universe from being a chaotic mess, where things happen before they are caused. So you see, this avalanche of discovery, starting with the apple falling in the orchard, then the moon falling around the earth, then Jupiter's moons being late, then the trains and the flashlights, and finally the structure of space-time itself. It shows us that the universe is a tightly woven fabric. The speed of light is the thread that holds it all together. It's not a nuisance. It's not a barrier we can crash through if we just build a better engine. It is the scaling factor of reality. It's the conversion rate between space and time. It's the assurance that there is a past, a present, and a future. And when you realize that, the number doesn't look arbitrary anymore. It looks like the most beautiful, necessary thing in the world. It's the structure of the stage we are dancing on, and without it, there would be no dance at all.